parallelize a program manually, we must avoid data races. And when a compiler parallelizes a program, it must, of course, also avoid data races. And the terminology that is used to describe this is that if there is a data dependence, then the code cannot be run in parallel. So in this case, there is a so-called true data dependence between S1 and S2. Since, well, I mean true, it means that the first statement here writes the value and the second reads the value. And it's written like this. And when we see this delta and some kind of dependence, we will see two additional that prevents parallelization and a third which does not prevent parallelization. They are the meaning of this delta is that the left statement or expression or loop iteration should be executed before the right. Okay, so these data dependencies, they are not necessarily only at statements at that level, but they can be between instructions. For instance, if we need to read A and B from memory, these two instructions must be executed before we can add them, obviously. And optimizing compilers, they create graphs to express this information, and then they try to schedule the instructions in a clever way so that the performance is improved. Okay, so we have data dependencies at the instruction level, at the statement level, as on the previous slide, and loop iteration level. And that's the focus of this lecture. There can also be dependencies between functions. Perhaps we can execute two functions, I mean calls of two functions at the same time, and do that and win some time. But then we have to determine whether there is a data dependence between them, which there could be if they modify some variable, or one computes a value that is used as an argument to the other, of course. There can also be between threads. And parallelizing compilers, as I have mentioned, it is usually between different loop iterations. Okay. So, if there are data dependencies between some loop iterations, it may still be possible to run the program in parallel. We will next see an example of that. Okay, but well, first we will just mention two terms. First of all, total order versus partial order. Integers they are totally ordered, since we can always compare which one is greater than the other if they are different. And a partial order, it is with elements that cannot always be compared. Okay, and if loop iterations of a for loop are a total order, it means in this context of this lecture that all iterations must be ordered, and then they must be ordered as in the sequential program. But it may be the case that some iterations must be ordered due to data dependence, but others may not be. And in that case, we can create a new loop, perhaps, and run some of the iterations in parallel. We will see a very concrete example of that in a moment. Okay, so one way to think about parallelization is to think of the items that we want to run in parallel as nodes in a graph. And then we want to do topological sorting. I will explain that if it's new to you on the next, very shortly. And try to, when we do this topological sorting, we can find which items can be run in parallel. Okay. However, this topological sorting is not done during compilation. It's just a way to look at parallelization. Okay, so the compiler does not enumerate all the iterations and select an order. Instead, it computes a new order. So it creates a new loop. Okay, and how to do that we will learn in this lecture. So let's look at an example. Here we have a so-called DAG. And that's a directed acyclic graph. And in this graph there are no cycles, and we can do a topological sort of the elements in this graph, and that means selecting a node which has no not yet scheduled predecessor. So at this point we can select either A or C. And if A takes longer time to perform, if it's a computer instruction, or it's a work item at a company or other organization, then it may be preferable to start the slowest operation first, so that we can start B as early as possible. Okay, so we can select A or C, and then when we have selected both, we can, then we must select B, and then we can select either D or an unknown E here. Okay, so now I need to, width, it should be 20. Hope I get that. Let's see. Okay. So we will now look at this topological sorting in a different context, namely in a double for loop. Okay, so let's look at this program and see if we can run the outer loop in parallel. Okay, so what happens? This statement, it reads a value written in the previous iteration of the I loop. Okay, that means we cannot run the I loop in parallel. Okay, maybe we could run the J loop in parallel. That is not for a multi-core, but for SIMD instructions, for instance. But let's see here. Now we compute the value which will be used in the next iteration. So we cannot run the inner loop in parallel either. There is no total order of the loop iterations. Okay, so what in this case? So now I have not written out the loop bounds, but just for simplicity, say they are starting with the iteration 0, and then we can have different iterations of the I loop. We can ignore that it's I minus 1, because this may point to this A could be a pointer in C, so that it still would be valid code. So just ignore that it would be negative there. Okay, and then the J loop. So in the sequential program, we would first execute this iteration. I mean, it's the first here. And then we would execute this, since, I mean, we increment j. So we would do that one, and then that one, and then that one. Okay, so let's now see the data dependencies between the loop iterations. There is a dependence between the j iterations due to this. So actually I should use a different color like that. So here is a data dependence between these two iterations. I mean, the iterations with I is 0 and j first 0 and then 1. Okay, and of course there are new dependencies between when j is 1 and j is 2, etc. So there are dependencies like that, and there are similarly dependencies between the iterations in the I loop. Okay, but are they in a total order, or is it possible to find parallelism in this? Okay, I didn't say in what, but we can view the iterations as nodes in a graph. Okay, so what we can do now is to start with this iteration, and then we can see this and this, they are not depending on any iteration in the same with the same loop variable. Okay, so these two can be run in parallel. Okay, there is no such loop here in I or j, so this is a new loop that is needed. And in the same way we can do this. Okay, and we can continue like that. So even if we cannot run either I or j in parallel, we can create a new loop, or two new loops actually. One that I mean, this would be an outer loop that does this first and then run this concurrently, and then moves on to the next and run these three concurrently. In the beginning there is no big point in doing it concurrently because there would be too much overhead, but when we have sufficiently many iterations to do at the same time, then it will improve the performance. Okay, so doing this in OpenMP would not work, since in OpenMP we can of course rewrite the source code so that it will have this loop, but we cannot specify it without changing the source code drastically. In OpenMP we can only say that this loop is fine to run concurrently. All iterations can start at the same time or in any order. But a parallelizing compiler can take the original sequential program and produce new loops that will run in parallel without data races. The person who invented this kind of parallelization is someone that all of you know, I think, namely Leslie Lamport. Who created the LaTeX macro package for tech. Okay, okay, that's what I was going to say about the viewing the loop iterations as nodes in a graph and finding which iterations can actually be run in parallel. So we need to reorder and create new loops. But initially, the compiler tries to run the existing source code in parallel by checking if there are data dependencies between the iterations in the outer loop. And if there are none, then it can run it as it is. If there are, then it will try to reorder the loop iterations.